So volume. Volume is defined as the space inside a three-dimensional object, just like you and I. Because we are three-dimensional, our body has volume. Now, over the years, you've learned volume formulas for some basic figures. For example, here's a here's a simple prism, length times width times height. And there's a formula for the volume of that. Here happens to be a globe. And with this particular globe, we can see it's a sphere. And the volume of a sphere is 4/3 pi r cubed. So there's formulas for kind of common shapes that we see, but if you begin to look closer, volume of other shapes are also important as well. For example, if I take this globe, and if you'll take a look at it, the intricate metal piece that is right here, well, it's actually made up of probably one, two, three, four shapes. One kind of resembles a prism here. One may be a cylinder, but these two right here, there's really not a formula for. But if you think about this area between curves idea, well, maybe we could get volume that way. Or we can think about volume of these figures that make up the base. Now, these are not your ordinary spheres or hemispheres because it looks like they've been made by maybe rotating around an axis. Maybe we've taken one shape and just spun it around an axis to make all of these right here. So that gets us into what's known as the volume of a solid of revolution. So, for example, take this rectangular piece of paper. And let's say that I were to rotate it around my finger and I were to rotate it this way. Well, think about what figure you are creating. Well, you've just created a cylinder. Okay, you've just created something circular. We can see that from the end because as this spins around, it's going to go a full 360 degrees around. But the question is, what if instead of putting my finger here and spinning it, what if I put it on my finger here and rotate it that way? Am I going to get a different figure? Well, the answer is yes, I will. In fact, let's go ahead and take a look at this a little bit further by looking at what I have on screen for you. So imagine we have a rectangle that goes from the origin up to this red line, across and down. So this rectangle is, let's say it's 10 by 3. And we're going to rotate it around an axis. In fact, we're going to rotate it around the x-axis. And you'll see we get this nice figure, this nice cylinder. And if we turn it to the side, we can see that that is completely filled in. We have created volume. And so that's the figure we get if we rotate that shape around the x-axis. But what if we were to take the same shape? We'll go up here from the origin to 3, all the way around to 10. But what if we were to rotate that around the y-axis this time? That's the shape that we're getting in this case. And in fact, what we're getting is we're getting two very different volumes. So what's different about these? Well, what's different about them is they are being rotated around an axis. That's true. But the radius is different. In fact, this figure is going to have a larger volume because its radius is 10 away from its axis of revolution. Let's see that again. Axis is 10 away. So this gap is always 10. Where, if I were to do the same thing here, let's try this again. As this is created, its axis is always 3 away. So what that leads us into is it leads us into this discussion about volume. Let's do this. Let me take an ordinary rectangle, much like you see there. And let's say we rotated it over an axis. Namely, we went this way. Well, that rectangle is going to spin at you, come around, down, and through, and come back again. In fact, what it's going to create is it's going to create this cylinder. Basically right there. Now, imagine if we had multiple rectangles with various heights, or the same height. What we would basically create is we create this concept of volume, much like what you see here. Now, if these all have the same height, we create a cylinder. So imagine for me, if you were to think about this, we're going to talk about what's known as a solid of revolution. And so to have a solid of revolution, it might look something like so. Let's say we have a region right here, much like that. And we want to take this region and we want to rotate it over this axis. So this axis is called the axis of revolution. It's what we want to spin it around on. Now, this solid of revolution is made up of actually a lot of parts. It's actually made up of a lot of rectangles of various heights. And I could kind of keep doing this all the way through. Now, one thing you'll notice is that this solid of revolution is fully attached to the axis of revolution. That's important. So when we talk about volume, we can find the volume of a solid of revolution, meaning we can take something that's two-dimensional, rotate it around an axis, and get something that's three-dimensional. Now, there's various ways you can calculate this volume because it's important. If you look underneath a car, I don't think we see a lot of shapes that it's like, ooh, sphere, ooh, prism, ooh, rectangular pyramid, whatever it might be. The shapes are very unique. And so when we talk about volumes of solids of revolution, we're going to talk and introduce you today to the first method. And that is what is known as the disk method for finding the volume of a solid of revolution. So let's take the example, the drawing that I have up here, and let's say that we have this boundary that will start at A, and we're going to end at B. And let's say this little curve up here is the graph of some function f of x. And we're going to rotate this region over the x-axis. So let me share with you the formula first, and then we'll talk about the y. So to find the volume by the disk method, and if we think about a disk, that right there is a disk. Okay, it is I guess a cylinder with a very small thickness. So volume by the disk method then is equal to the integral from A to B of the function all squared with respect to x. Now let's talk about the pieces of this formula here. Now imagine again that we have all these rectangles that we have. Now what we're doing is we're taking basically a rectangle and rotating it around an axis. It's going to again give us this right here, this disk. So if we think about this disk, basically this disk, it has a volume based on its area and its thickness. So this is a circle, and the area of a circle is pi r squared times its height. Now, if you take a look at our formula inside the integral, because there's one thing that I have not put in the formula as of yet. This r squared, well, if we think about a rectangle and it's rotated around an axis, well, this is basically the radius, isn't it? And a rectangle right next to it would have a different radius, and so on. So this part here is basically the radius squared. This dx is the change in x. It's basically this width right here. And all of these rectangles have a very, very small width. This is our height. The only thing that I'm missing from my disk method formula is the pi. And so I've left it off for just a moment because where can you put the pi? Well, pi is like it's a coefficient. So when we deal with integrals, pi can go inside, can also go outside. So we can write it like that. We can also write it inside of here, but we do need pi. So pi r squared times h is the volume of a cylinder. And a cylinder can also be thought of as a disk. And if we stack all of these disks together, and if we add up all of these in theory volumes, we have the volume of the solid of revolution. And that's what we're going to talk about as we proceed. The volume of the solid of revolution by the disk method. We'll continue in our series next time.